There is an object in the universe that does not behave like a star. It does not shine steadily. It does not remain calm. It spins so fast that normal matter should be ripped apart. It is born from death. It compresses the mass of a sun into a sphere the size of a city. And according to everything physics predicts, it should not be able to exist like this for long. So what happens when a star dies, but refuses to disappear, and instead becomes one of the most dangerous objects in the galaxy? And if physics says it should already be gone, what exactly are we looking at right now? When we think of a star, we usually imagine a stable, shining object powered by steady nuclear fusion, producing the light we see in the night sky. But the object scientists are watching does not behave according to that pattern. Invisible light. It is not especially bright, and can even appear faint, easily overlooked without specialized instruments. Its strangeness is not about brightness, but about its physical state. It is no longer sustained by nuclear fusion, nor does it exist in a calm equilibrium. What prevents it from collapsing or tearing itself apart is not a fresh energy source, but a fragile balance between extreme gravity and an astonishing rate of rotation. It spins so rapidly that, if it were possible to stand on its surface, the ground beneath you would be moving at a speed approaching that of light. For any ordinary form of matter, centrifugal forces at such speeds would be enough to rip it apart. Yet that does not happen, because its gravity is far beyond anything we experience. A mass comparable to the Sun, compressed into a region only a few tens of kilometers across, generates a self-gravity strong enough to hold everything together, even as the object tries to tear itself apart through rotation. It is this sustained tension that makes it anything but quiet. It emits regular signals, repeating bursts of energy with almost perfect precision, as if the universe itself were marking time with an extreme machine. When you encounter an object that does not need to shine brightly to be dangerous, does not need to explode to matter, but simply exists by balancing on the edge of physical laws, what is it really? When a sufficiently massive star reaches the end of its life, its death is anything but gentle. As nuclear fuel in the core runs out, the pressure that once countered gravity disappears, and the core begins to collapse under its own weight. This collapse happens in an instant, triggering a violent rebound that blasts the outer layers of the star into space in a supernova. One of the most violent events the universe can produce. But the crucial part is not the explosion itself. It is what remains afterward. As the light of the supernova fades, the crushed core does not vanish. It contracts to an extreme state, forming a new object that is astonishingly small yet unimaginably massive. This remnant is known as a neutron star. It is only about 20 kilometers across, roughly the size of a large city. Yet it contains more mass than the Sun itself. At such densities, matter no longer exists in the atomic form we are familiar with, as electrons are forced to merge with protons, creating a dense sea of neutrons where the space between particles nearly disappears. And in this extreme state of matter, if you were to take a single teaspoon from a neutron star and place it on Earth, that tiny amount would weigh more than 1 billion tons, outweighing every building, every road, and every city humanity has ever constructed, all compressed into a volume no larger than the tip of your finger. And here lies the paradox. Intuitively, an object that has already survived the death of its parent star, compressed beyond the point of further burning or explosion, should be a quiet remnant. Yet a neutron star is not a harmless stellar corpse. Its extreme density, immense gravity, and exotic state of matter mean that this death is not an ending, but the beginning of a different kind of danger. If this is what remains after a star has died, Why is it still watched so closely? And what makes a stellar corpse a potential threat? When a neutron star rotates, it does not simply spin in space. Its intense magnetic field channels high-energy particles along the magnetic poles, producing narrow beams of radiation that shoot outward into the cosmos. These beams do not radiate in all directions. Instead, they sweep through space like the light of a lighthouse. And when Earth happens to lie in their path, our instruments detect regular, repeating signals, brief flashes known as pulses. This is where the name pulsar comes from. They do not truly pulse in the way a heartbeat does. The rhythm is an illusion created by geometry and rotation. When the first of these signals was discovered in 1967, it caused genuine confusion. The radio pulses arrived with astonishing precision, repeating so regularly that they resembled an atomic clock placed in deep space. The discoverer, Jocelyn Bell, and her team even had to consider a bold possibility: whether the signals might be artificial, originating from an extraterrestrial civilization. In the end, the explanation turned out to be even stranger than aliens. These signals came from dead stars, compact and extreme, spinning faster than anything humanity has ever built. Some pulsars rotate hundreds of times per second, faster than helicopter blades, faster than jet engines. And they sustain these speeds not for minutes or years, but for millions of years. At such speeds, intuition suggests they should have torn themselves apart long ago. Yet they do not. And here, an unavoidable question emerges. What allows an object spinning this fast to remain intact? Not all pulsars exist alone in space. Some have companions. Smaller stars locked into tight orbits by the immense gravity of the neutron star. And in these systems, the balance is never equal. Over time, the pulsar's gravity begins to pull material away from its companion. That material does not fall straight in, but spirals inward, forming a superheated accretion disk that orbits the neutron star. Within this disk, gas is compressed, collides, and accelerates until it glows intensely before finally falling onto the neutron star. Each fragment of infalling matter carries angular momentum, and this leads to two simultaneous consequences. First, the pulsar spins faster, like a figure skater pulling their arms inward. Concentrating mass closer to the center increases the rate of rotation. Second, the pulsar becomes more massive. The mass increases gradually, but for an object already near physical limits. Every added fraction matters. Meanwhile, the companion star pays the price. It is not consumed all at once, but eroded slowly. Its outer layers are stripped away. Streams of superheated plasma pulled off, as if the star were being eaten atom by atom. This process is why such systems are known as black widow pulsars, named after the spider that consumes its mate. The analogy is not exaggerated. The pulsar survives, growing faster and heavier, while the companion slowly fades away. And as this process continues, a problem becomes increasingly difficult to ignore. Is there a limit that no amount of spin or stolen matter can ever overcome? Among all the pulsars ever discovered, one stands out in a way that makes physicists pause longer than usual. It is not remarkable because it is close, nor because it shines brighter than others, but because the numbers associated with it should not coexist. This pulsar spins at roughly 707 rotations per second, meaning that in the time it takes you to blink, it completes hundreds of full turns. Its surface moves at a significant fraction of the speed of light. But speed alone is not what truly makes it unusual. What draws more attention is its mass. Measurements indicate it weighs about 2.4 times the mass of the Sun, all compressed into a region only about 20 kilometers across. The problem is that according to current physical models, a neutron star with that much mass should not remain stable. There is a theoretical boundary beyond which neutron pressure can no longer counter gravity. That boundary is known as the Tolman-Oppenheimer-Volkoff limit. And this pulsar is uncomfortably close to it, with just a bit more mass, or a slight loss in internal support. Its structure could fail. By ordinary reasoning, an object like this should have crossed that limit long ago and collapsed into something else. Yet it is still there. Still spinning, still emitting regular signals as if nothing were wrong. This persistence is what turns it into a warning file of the universe. It does not break the laws of physics, but it pushes them to their very edge, where even the smallest deviation could have irreversible consequences. And when an object exists in defiance of what models predict, the question is no longer what it is doing, but what physics will do next. When an ordinary star dies, the universe leaves behind a clear signature. A supernova flares into existence. Shockwaves spread outward, and light can be seen from across the galaxy. But the death of an overly massive neutron star does not follow that script. If a pulsar like PSRJ 9520607 crosses its final limit, there is no new explosion. There is no flash of light. No expanding cloud of debris. No visual warning that something has ended. Instead, the death unfolds in near total silence. The only change is absence. The regular pulses that were once detected vanish. The radio signal, stable like a clock, abruptly stops. In that moment, the neutron star does not explode. It collapses inward on itself. Matter already compressed to extreme limits crosses its final threshold, and a black hole is born. Cleanly and efficiently, with no outer layers left behind to observe. From the outside, there is nothing to see. Yet physically, the event is not entirely invisible. Such a sudden collapse can produce a brief signal of a different kind. Not light, but ripples in space and time themselves. This is why gravitational wave observatories, such as LIGO and Virgo, alongside NASA's monitoring programs, are designed to hunt for extremely short rows. Non-repeating signals. Fleeting disturbances that may be the only evidence of a silent collapse. If detected, such gravitational waves would not only confirm the birth of a new black hole, but also offer a rare direct glimpse into the moment a neutron star crosses the ultimate boundary of physics. And what makes this scenario unsettling is not what may happen, but what may have already happened. If this pulsar collapsed silently thousands of years ago, we would still be observing its past version, unaware that the real story may have ended long ago. There is a fundamental truth that is easy to forget when we talk about danger in the universe. Nothing we observe happens in real time. Everything we see already belongs to the past. This pulsar is located roughly 14,000 light-years from Earth, which means every signal we receive today was actually emitted 14,000 years ago. The regular radio pulses, the measurements of spin and mass, all of them are slices of the past, delivered to us with an unavoidable delay. That opens an uncomfortable possibility. The star we are monitoring may have crossed its final boundary long ago. Its silent death could have already occurred, with the information still traveling toward Earth. If that is true, then what we are seeing is not a pulsar spinning in the present, but the last breaths of an object that no longer exists. From the universe's perspective, there is nothing unusual about this. Light and radio waves always carry the memory of past events. But from a human perspective, It creates an unavoidable paradox. We are tracking a potential threat, without knowing whether that threat still exists or ended thousands of years ago. And if that death occurred silently, without light or explosion, the question is no longer simply when it will happen. The deeper question is this: if we do not yet know it has ended, can it still be considered a threat? Up to this point, every danger we have discussed has been tied to motion. Pulsars must spin rapidly, emit beams of radiation, and maintain a constant state of tension. But there exists a type of neutron star that requires none of this to be dangerous. They do not need to spin fast. They do not need a companion star to sustain their extremity. Their danger comes from something else, a property so intense that it overwhelms everything else. These objects are known as magnetars. They possess the strongest magnetic fields ever observed in the universe. Fields so powerful that familiar physical concepts begin to break down. For comparison, Earth's magnetic field is strong enough to guide a compass needle. A typical neutron star already has a magnetic field trillions of times stronger. Magnetars go far beyond even that, strong enough to distort matter at the atomic level. The danger of a magnetar does not lie in constant activity, but in moments of instability. When magnetic stress builds up within the rigid crust of a neutron star, it can be released suddenly in violent outbursts. A striking example occurred in 2004, when a magnetar on the far side of the galaxy released a gamma-ray flare so intense that it disrupted satellites around Earth. Despite being tens of thousands of light-years away, that event forced scientists to view magnetars not merely as rare astronomical curiosities, but as potential hazards on a biospheric scale. Models developed by NASA and the astrophysics community suggest that if a magnetar close enough were to produce such a flare, it could damage the ozone layer, disrupt DNA, and trigger severe cascading effects in marine ecosystems. No visible light is required. No early warning is needed. A single moment of instability is enough to produce planetary-scale consequences. And what makes this idea truly unsettling is this: if a magnetar like that were not so far away, but closer, what would happen then? So far, every danger we have discussed has remained safely distant, thousands or tens of thousands of light-years away. But to understand why that distance matters so much, consider a simple thought experiment. Imagine a neutron star, not even a magnetar. It's an extreme pulsar, placed near the orbit of Jupiter. That distance still feels vast on a human scale. But within the solar system, it would represent a massive disruption. Immediately, its gravity would begin to disturb the familiar order. The orbits of the gas giants would be perturbed, and that instability would slowly propagate inward, toward the delicate balance that keeps Earth in its path around the Sun. But gravity would only be the beginning. Such a pulsar emits continuous beams of high-energy radiation. If Earth were caught in their path, the ozone layer would be the first line of defense to fail. As ozone diminishes, ultraviolet radiation from the Sun reaches the surface, and space-dependent technologies begin to suffer. Satellites malfunction, GPS loses accuracy, and global communications become unreliable. And that scenario involves only a pulsar. If the object near Jupiter's orbit were a magnetar, the rules would change entirely. A magnetar does not need rapid rotation or precisely aligned beams to cause damage. Its magnetic field alone, if close enough, could directly affect matter and the surrounding environment. At such a distance, it would not need to touch Earth. Its mere presence would be enough to disrupt the natural and artificial systems on which modern life depends. This thought experiment is not meant to predict the future, but to clarify a fundamental point. Earth is safe not because the universe is gentle, but because we are far from its most unforgiving objects. So, what is truly protecting Earth? After everything we have discussed about neutron stars, about radiation, magnetic fields, and gravity capable of destroying planets, it seems reasonable to assume that nothing could survive near such objects. Yet the universe once again defies our intuition. Astronomers have discovered that some pulsars are still orbited by planets. One of the most famous examples is the pulsar system PSRB 1257+12, where at least 3 planets have been confirmed. Remarkably, these were also the very first exoplanets ever discovered. The existence of these planets raises a fundamental question. A supernova should have wiped out everything nearby. That means these planets either formed after the catastrophe or condensed from shredded remnants left behind. In either scenario, the environment they inhabit is unimaginably harsh. There is no steady starlight, no familiar day and night cycle. Instead, bursts of high-energy radiation sweep through space with the pulsar's rotation. If life exists in such places, it cannot resemble anything we know on Earth. It would have to hide deep beneath the surface, shielded by kilometers of rock or ice, far from direct radiation. It would also have to adapt to a world without natural light, where energy does not come from photosynthesis, but from chemical or thermal sources deep within the planet. These planets are not ideal places for life, but their existence reveals something important. Even beside the universe's monsters, matter can reorganize, time stabilize, and persist in unexpected ways. And when we realize that life, if it exists, may still find a foothold in the harshest environments imaginable, another question begins to take shape. If life can exist there, alongside some of the most dangerous objects in the galaxy, then what does safe really mean? So, after everything we have explored, the original question still remains. Should we be afraid of the most dangerous stars in the galaxy? The answer is no. Not in the Hollywood sense. Not as an approaching doomsday. These objects are indeed dangerous, but they are also very far away. That distance is what has protected us for billions of years. And so far, it continues to do its job. NASA and scientists do not watch these stars out of fear. They watch them because these are rare places in the universe where matter is pushed to its ultimate limits. They are places where relativity and quantum physics are forced to coexist, where familiar models begin to strain, and where the most fundamental questions about space, time, and matter are tested. These stars do not simply show us how dangerous the universe can be. They reveal how the universe behaves when pushed to its final boundaries. And perhaps the most important thought is not whether a star could ever kill us. It is that we live in a corner of the universe so rare and so quiet that life is able to exist, evolve, and ask questions about its own origins. If stories like this help you see the universe a little more clearly, consider subscribing to the channel so we can continue exploring the limits that science is still trying to understand. Thank you for watching, and I'll see you in the next journey, where the biggest questions often begin in silence.